The next thing we looked at was greedy algorithms, and we specifically focused on greedy algorithms that solve problems well. So greedy algorithms. All right, so a greedy algorithm is one that does the following. So first, it builds a chunk in, it builds a solution in steps. So build solution in steps. At each step, we do three things. So one, we improve the value of the solution. So at one, we are locally optimal. So locally optimal means that we look at what we have, at the options we have available to us. We have some kind of objective that we want to accomplish, and we improve the value of that objective as much as we possibly can in one step. So this is the one where we say, I'm pretending the world is ending tomorrow, so I'm going to do the best I can. Like maybe someone's about to pull the plug on my computer, so let's solve this thing as close as we can get it. All right, so 2 is feasible. This is the easy one, right? We're not going to allow stepping outside the rules of the problem on a path to get to the solution we want. We want every single solution, every single stage of the algorithm to have a feasible solution. And then 3 is irrevocable. So in other words, there's no possible way to walk back a step that I've taken. Okay? So these algorithms, I like to say, tend to be fairly easy to design, but fairly hard to show if they're optimal. So I'm going to work the example from the homework that we did with the compatible intervals and just kind of give you a sense of how I would approach this problem. All right, so let's work the example from homework. All right, so you're given a collection of intervals. So let's write this down. Given intervals A1, B1, A2, B2, A3, B3, and so on, all the way up to A and Bn. We want to pack as many together as possible so that they don't overlap, right? So what is the largest set of these, largest subset of these intervals that doesn't overlap at all? Is the largest subset of intervals that don't overlap. All right, and what we're going to do is we're going to try 3 different greedy algorithms. So 3 greedy algorithms. All right, so the first one is earliest start first. All right, so what does this mean? The earliest start first means that we're going to look at these intervals. We're going to sort them by start time, and then we're going to take the one that starts first and put it in our solution, and then go down to the next one. And if it's compatible with the one we just saw, we'll put it in our solution. If it's not, we'll skip it, and we'll just keep on going down the line. Every time we find an interval in this sorted list of intervals, we're gonna check to see if it's compatible and put it in if it is, and not put it in if it isn't. Okay, so that's earliest start first, and notice the first means to be scheduled, like to be considered for scheduling. Okay, there seemed to be a little bit of confusion about that on the homework, but this means the first one to be considered for scheduling. We're still going to consider all the intervals for scheduling, right? Just because I consider one first and it's incompatible with something that happens earlier or something like that doesn't mean that I forget about the earlier ones. All right, now shortest duration first is the second one. Shortest duration first, and then last we're going to do earliest finished first. Finish first. Okay, so for 1, why is 1 not optimal? So why does 1 is not guaranteed to give us the right answer? Well, it's because of things like this. I could have a whole bunch of small intervals that are all compatible with each other, and everything is great, and then one giant interval that is incompatible with all of them, but has an earlier start. Okay, so thinking about it like trying to schedule something with an early start first feels like a good idea, because it makes sure that you don't, because maybe something that starts early finishes early, but it doesn't work necessarily because you end up blocking all of the rest of them. So this is bad. All right, so 2 doesn't work, and why does 2 not work? 2 actually works better than 1, so 2 can't hurt us quite as badly as 1 can hurt us, but 2 doesn't work because we could have something like this. We could have 2 long intervals that go like this, and then 1 short interval here that overlaps both of them, right? So then this interval here would exclude the scheduling of those 2 intervals above it, and so we don't want this one. This is also bad. Notice that 1 interval can only now exclude 2, right? I can never have 1 interval exclude more than 2 intervals, right? Otherwise, the other intervals would be shorter than it, and it wouldn't be excluding them. Okay, so this is another one where there's this heuristic that says a short duration interval feels like it ought to be able to pack more in, but that's not necessarily the case. It's just the wrong intuition. All right, so last is earliest finished first. Earliest finished first is optimal. So it turns out this actually is guaranteed to always give us the right solution. And so let me give you some intuition about why this works. And so this is going to be kind of a condensed proof of why earliest finished first is an optimal algorithm. So why? Let me give you the proof sketch. Okay, so what I'm going to do is I'm going to say, suppose the greedy algorithm gives us this set of intervals. So G equals G1, G2, G3, ... all the way up to G, let's call it, I don't know, K. Okay, so this is the greedy solution. And then let's let O, the optimal solution, actually, let me do this. Let me see how do I want to do this. Let me actually let X be any solution that doesn't use the first greedy choice. X is something else. So it's X1, X2, ... all the way up to XL. And this is any solution that isn't the same as the greedy solution in element 1. So any solution that doesn't use G1. Okay, so all I'm doing here is I'm focusing on the first thing the greedy algorithm chose to put in. And so now what I'm going to do is I'm going to show that I can put G1 into X without making it worse. Okay, so what that will do is it'll tell us that without loss of generality, the first thing the greedy algorithm does is a good idea. Okay, any solution that doesn't agree with greedy on the first choice might be worse than greedy, right? Cannot be better than greedy. All right, so let's do this. So now there's 2 cases. So here, let me just give you the goal. So show that we can put G1 into X without making it worse. Right? Really quite a simple concept and extremely easy in execution, right? Really easy to see why this proof works. A lot of the proofs that people found on the internet you posted, or that you were inspired by on the internet and you posted in the homework, are actually much harder to think through, right? Much less easy to reason about. This is super easy though. Here we go. So, okay, I'm looking at X and I'm looking at G, and I want to say I can take X and make it closer to G, like just put G1 into it and make it better, or at least not make it worse. So case 1 is the easy case, the really easy case. Case 1 looks like this. Here's G1, and here's X1, and here's X2. ... Right, so case 1 is that G1 does not conflict with anything in X. G1 has no conflict with X. Well, in this case, I can just put G1 directly into X and not change anything, and now X is better. So put G1 into X. Now, X is better. Okay, so what's the other case? There's actually only one other case here. The other case is that G1 conflicts with the first thing in X, right? So G1 G1 could look like this. Dot, dot, dot. All right, so in this one, there is a conflict, but there's only a conflict with 1. And so now what I can do is I can remove x1 and add g1. Okay, so now this new thing I made, this new solution I created, is no worse, right? It's not better, but that's fine. We don't need to show that it's better. We just need to show that it's not worse. So the new solution is not worse. I called this case 1. Feels silly. I know no one's going to see these notes, but I got to keep it. I got to make sure I correct the error. So the new solution is not worse. Okay. Why is this the only case? Why are these two the only cases? So you might say, well, how come we don't have to consider a case where G1 conflicts with more than one interval in X? Well, if G1 conflicted with more than one interval in X, then that would mean some other interval in X finishes sooner, right? So we'd have to have something like this. G1, and then maybe X1 here, and X2 here, right? Now G1 is conflicting with both of those, but this is not possible because in this case, the greedy algorithm would have chosen X1, right? So G would contain X1. All right. So there we go. Turns out that's the proof, okay? So why is this the proof? So what I just showed is something quite simple. I showed that I can take G1 and put it into X without making X worse. So I can take any possible solution to this problem, and I can put the first thing the greedy algorithm did in this solution. Okay. So now once I've done that, let me ignore everything that happens before the finish of G1, and now let me look at the subproblem that starts at time starts right when the G1 interval ends. And now that's a new problem. It's a new subproblem of this whole thing. So now whatever X looks like after that, I can do the same thing again with G2. And I can add G2 into this sub X and make it better. And then I can add G3 into this sub X and make it better. And I can just do that iteratively, or inductively if you want, until I've made X into G and possibly improved its objective value. Right? So we can now do this. Let's just say iteratively, transforming X into G while not making it worse. This is a common way we want to think about greedy algorithms. Right? We want to have some kind of argument that the first choice the greedy algorithm makes is a good choice, and that propagates, right, in such a way that things get better and better and better. All right.